Hi, in this video we're going to be looking at nuclear power and how that all works, alright? So that's what we're going to be doing, and we're going to be looking at the fission power station today. So the statement, only nuclear power plants in Russia and Japan are unsafe. How do you think about that particular statement? Well, if you did some research, you'd find that yes, Russian power stations, many of them are really, really old. The Fukushima power station that had the disaster with the tsunami, that was actually going to be decommissioned fairly soon anyway. But I think you'd find that if you went all around the world, there would be lots of potential dangers with all nuclear power stations. All right. Now they have been developing a new fission power station called a pebble reactor. And I'll show you a video about what that looks like. But generally, when you're doing nuclear power, it is an unsafe. It can be unsafe or it can be quite safe. And there are many safeguards that are put in there to try and make it as safe as possible. But the thing is, we live in a world of terrorism. Who knows what could happen? So like if they blow up a coal power station, it's just going to be a disaster. But you're not going to have long-term effects. But if they blow up a nuclear power station, you've got all this radiation that's going to be around for a long time. So, it's not for me to preach, but for you to form your own views about all this stuff. Anyway, I'm going to move on to the fission process. So the fission process has some stages. So the first thing is you need a critical mass. We enrich uranium-238 with uranium-235. Okay, and they're generally about 5%. Of that is what's required, and the reason being is uranium-238 doesn't easily fission, where 235 does. So the mass required for a chain reaction to be self-sustaining is what we call the critical mass. The controlled chain reaction, that says that every reaction will cause another nuclear fission reaction. And I'll talk about how you control the reaction itself later in this video. The moderators, the moderator, normally heavy water, is used to slow down the neutrons. And it does that by not absorbing the neutrons, but actually having collisions with the neutrons and slowing them down so they can get encapsulated inside the nucleus. And then we have control rods, and their job is to absorb extra neutrons. And normally made of boron or cadmium. Right? So they're the sort of elements that are used for that. Alright, so basically what happens inside a nuclear fission, we're turning a heavy nuclear fragment into lighter fragments, okay, or more stable ones. So generally starting with uranium-235, alright, put in a nucleus, gets inside the nucleus, and then splits that particular nucleus into two other smaller nuclei, and then we also get some neutrons being produced. Now this is just one of the reactions that can occur. On average we get about 2.5 neutrons released. Now those 2.5 neutrons go on and cause the same sort of reactions to occur. Alright, so there's many of these fissions, possible products that could actually occur. What happens? Again, it's a random process, so you don't know what can actually happen. Alright, so the thing about the actual atom itself, it becomes really elongated, becomes really big, and so therefore we get these strong coulombic forces now overtaking the strong nuclear force, and that's why it splits. And these products over here are radioactive generally, alright, so that's the danger of that. So how does the reactor work? Well, you've got the core, okay, so it's generally shielded by basically thick concrete, lead, all those sort of things. You have your fuel rods, right? So these fuel rods are generally made up of that uranium pellets, but it's a process, right? Graphite moderator slows down the neutrons. So heavy water, okay? So heavy water, all those things are really important. So the moderators don't absorb the neutrons, but they slow them down. Right? We have these things called control rods. They can be moved up and down. And what they do is they allow the absorption of neutrons. So if you want to slow it down, you absorb more neutrons. If you want to speed it up, you absorb less neutrons. And then we have coolant system going in and out. So that's actually a sealed system going in and out of there. All right, so that's exchanging the heat, because that's really what it does. It heats up, gets really, really hot, heats up the water, produces steam, turns a turbine. So not really all that much different from a coal-fired power station. Good question here is, how much fuel does a 300 megawatt power station use? And I believe that's about enough to, look after about 10,000 homes. All right, so when we're looking at this, so 1 watt is defined as 1 joule per second. All right, that's what 1 watt is. So 300 megawatt is 3 by 10 to the 8 joules per second. That's what we're putting there. Now we're going to convert that to how many joules per day. So that's that figure. And then how many joules per year. So it's 9.46 by 10 to the 15 joules per year is what we're producing. Coming to the most famous equation, I suppose, of Einstein, E equals mc squared. All right, so E is the energy, M is the mass defect, or the difference in mass there, and C is the speed of light squared. So rearranging that formula to work out the mass, E divided by C squared, we're going to plug in our values, and it works out to be 0.105 kilograms. That's amazing, isn't it? So it's a really efficient process. Now, you can imagine a 300 megawatt power station burning coal. It's going to go through thousands of tons, millions of tons of coal to do the same thing. So, it's a really, really important process. It's a really quick process. Anyway, we're going to be looking at some other stuff in the next video. But this is basically how fission works.